Hello, folks. There have been a few issues that people have been having on trying to use the program, especially with the Charles Law portion. So I just wanted to go over just a couple things with you. What we found on the Charles Law portion of the program is you're only going to be able to put about 25 to 50 molecules in there. And I'd probably recommend the lighter ones. So if you put in about, I'm going to put in about 30 molecules into the container. You got to have some molecules in there. I'll put in 35. Yeah, I like a round number. Let's go 40. And then what we want on the Charles laws, we want pressure held constant. I'm going to go ahead and get my ruler out. I want to talk about that for a moment. And if you'll notice this box, all we can measure are you can move the ruler around, is you want to get to the inside lining of the box. And you'll notice that's somewhere. And look, watch Scooby. He will move. This is not a perfect program. It tries to simulate reality as much as it can. So what you're going to have to do is hopefully you can find a place where he gets sort of settled in after you let it run for a little bit. He's kind of going everywhere, but that's kind of looking like maybe that's about an average. So you can go in and hit this button, stop action it, get your measurement. So I've got about 6.6 there, it looks like. Now remember, this box also has a height and a depth. Height of the box is 5 units. The depth of the box is 5 units. The height is 20 units. No, that doesn't sound right. It's 5 tall and it's 20 deep. So if you take 5 times 20, that's 100. To get volume, it's length times width times height. So take 100. All you have to do is take whatever measurement you make here and multiply by 100, and that will be your volume in cubic nanometers. So in this case, we have about 6/10 here. So we're at 660 cubic nanometers. Now, here's the issue with the software, and the issue is, I'm going to go ahead and start this back up. If I start to raise this temperature very much at all, you'll notice that Scooby goes to the end of the screen. If Scooby gets to the end of the screen, and if you change it again and he doesn't move, then that data's done. Scooby is maxed out here. So that piece of data I just changed it to there is worthless. So I'm going to take away a little. What you want to see is you want to see Scooby still move. And if you'll notice, that didn't do it. So what we've found is you have to keep the temperatures fairly cool and the number of particles fairly low. So I've got this down to 405 and it's still not coming off the end of the screen. There we go. Now that's a piece of data I can collect where he is on the screen. So you can kind of find out where you're going to max him out. This should expand again. And that's okay as long as he's moving and not pinned against the screen. It's a legitimate piece of data. We've also found you can get it so cold, there is a minimum limit to the box's length. Let's take him all the way down here, and notice if I stop about here, let's see if we can make it any smaller. Notice when I'm cooling it, it can't get any smaller. So that's not a legitimate piece of data. Scooby needs to be moving. Let's see if that did anything. Nope. He needs to be able to move. That didn't do anything. Oh, now he's moving. So you want to collect your pieces of data on this so that Scooby has a legitimate measurement that if you change it, he will move. If he's pinned at either end, your graph is not going to look right. You're going to get things on your graph that are not going to be true when you graph it. And we will have discussed the graphs previously in class just a little bit. I don't know how much we got to, but we talked a little bit about the graphs, and there's model graphs online for this. So if you take a look at this thing, you should be able to get some good data with that, and you can put your data in to make a graph out of it. But if you cannot, I'm going to try to get his measurement here. That looks pretty legit. So if I move that in at this point, looks like it's about 2.4 nanometers. nanometers times 100, 240 cubic nanometers. Then I can graph that against, the pressure will be against that the volume. And then you should be able to get the relationship between the two. Pressure and temperature, I'm sorry. So as long as the box is moving, I'm sorry I said that incorrectly again, you want the volume and the temperature, the pressure should be constant. And when I say constant, you have to watch that. It's around 0.2. It'll fluctuate a tiny bit. Constant here means nearly the same. It's not going to always be exactly the same. Let's take him up a little bit. And you'll see it's staying at about 0.2. So that's why he's continually adjusting this to try to get that pressure to remain constant there. And the temperature went up, and you can see what happened to the box in terms of that. So that should get you through it. Just want to make sure that you get legitimate data. By the way, this would work on any of the other things that you're testing. You cannot collect data where Scooby is pinned against either side of the box. See you next time.